Hello everyone, my name is Bo Zhao. I'm from Humboldt University of Berlin, Germany. Today, on behalf of my co-authors, I'm going to talk about load shedding for complex event processing, input-based and state-based techniques. Complex event processing systems continuously evaluate queries over high-velocity event streams. It usually defines a sequential pattern of events, which are correlated by value predicates within a time window. There are a lot of applications, including finance, fraud detection, smart grid, transportation, and Internet of Things. CEP requires low latency and high throughput. We explain a CEP query by an example of bike sharing in New York City, where users rent bicycles through a smartphone application. They search bicycles at nearby stations, start rides, finish trips, and log bicycles at destinations. Bikes may quickly accumulate in certain areas. Therefore, the operator moves around 6,000 bicycles per day among stations. To improve operational efficiency, we detect hot passes of trips. The operator should relocate bicycles among hot passes. This query specifies a pattern that the previous trip's end station is the next trip's start station within 1 hour. One hot pass is illustrated in this figure. CEP query is stateful. It maintains a set of partial matches per query. State may grow exponentially in the number of processed events. It may face dynamic workloads, where input streams may change by orders of magnitude during short peak times. Therefore, the number of partial matches may easily change by orders of magnitude, as demonstrated in Figure 2. And this overall situation is very hard to predict. This makes low latency evaluation very challenging. To solve this issue, there exist a lot of optimizations, including parallelization, pattern sharing, efficient intermediate representation for partial matches, and semantic query rewriting. However, they have the limitation that it is difficult to pre-allocate resources for unpredictable short-time spikes. As a consequence, exhaustive low-latency evaluation may become infeasible. Therefore, we consider lossy optimizations for best effort evaluation. They usually discard some input tuples. However, dropping input tuples usually generate low-quality results. We illustrate this issue by the same example of hot pass detection in bike sharing. A bike trip is denoted by a pair of start station and end station. Trip from 5 to 8 at time point 1 contributes 0 complete matches. This input tuple should be discarded. However, we want to keep the same trip at time point 5 because it contributes 2 complete matches already for time window 2, 3, and 4. We now define the problem of CEP load shedding. It is to ensure that when evaluating a CEP query for a stream, it holds that the latency is below a predefined latency bound, and the lossy result caused by load shedding is minimal. We can perform input-based and state-based load shedding. An input-based approach has cost granular control of shedding impact. However, it saves more computing efforts because it directly discards input tuples without generating any partial matches at all. State-based load shedding, on the other hand, discards partial matches. It has fine granular control of shedding impact. However, it saves less computing resource because a partial match has already consumed some computational efforts. Hybrid load shedding has a potential to combine the advantages of both input and state-based load shedding. To perform the load shedding, we need to solve 3 problems. The first problem is to decide when to trigger the load shedding. This is solved by monitoring CEP system to check whether the latency is above a predefined latency bound. The second and third problems are what and how much data to discard. This is achieved by a cost model and the shedding set selection algorithm based on that. The cost model considers two aspects of a partial match, its contribution and consumption. Contribution assesses the contribution of a partial match to the query results. It is defined as the number of complete matches derived from it. Consumption assesses the computational resources consumed by a partial match. It is defined as the computational resources for all its derived partial matches and complete matches. Partial matches in different states may have different computational resources. We now introduce how to select the shedding site. For a partial match, we consider its relative consumption as the ratio of its own consumption to the consumption of all the partial matches. It is linked to latency saving. Loss of complete matches is its contribution value. Therefore, we define the shedding site selection as an optimization problem. That is, we select a set of partial matches that minimize the overall contribution value, but subject to the condition that the overall relative consumption is below the relevant extent of latency violation. This is a kind of knapsack problem, which is NP-complete. It should be noted that any decision of load shedding must be made instantly. Therefore, we discuss some optimizations, especially to significantly reduce the search space. To this end, we consider the granularity of cost models and lift it by temporal abstractions and data abstractions. For temporal abstractions, we divide the time window into several intervals, or time slices. Consumptions and contributions are computed per time slice instead of per time point. Similarly, data abstractions observe partial matches of overlapped attribute values may have similar consumption and contribution values. Therefore, we lift the cost model to classes of partial matches instead of individuals. After this, we generate state filters and input filters to perform actual load shedding. State filters are generated directly from the partial match shedding site as a lookup table. Input filters are derived from partial match site by cross-checking the event schema and value predicates of the query. There is a major problem of computing contribution and consumption of partial matches. That is, they can only be computed in retrospect because we are talking about computing something in the future. Therefore, we need to estimate them. To this end, we first estimate the cost model offline and then adapt it online. For offline estimation, we record historical partial matches and complete matches. Based thereon, we derive contribution and consumption values for each partial match. After that, we perform clustering for partial matches based on such contribution and consumption values per time slice. The contribution and consumption per cluster are computed as the 90th percentile of the values of partial matches within that cluster. We keep a map of cluster labels and these values. To use such estimates in online processing, we train classifiers of the partial matches of the clusters, one classifier per state. The classifier uses the attributes values of partial matches that appear in the query predicates. For online adaptation, initially we start with classifiers obtained from offline estimation. However, the contribution and consumption values may change as time goes by. Therefore, we monitor and update these values by streaming counts, such as sketches. We maintain the contribution and consumption per class by a lookup table for each state. We evaluated 6 queries of 2 synthetic datasets and 2 real-world datasets. We compare our hybrid load shedding with 4 baseline approaches: random input shedding, selectivity-based input shedding, random state shedding, and selectivity-based state shedding. We measure result quality as recall and throughput performance under strict latency bounds. we implemented a CEP engine in C++. Evaluations of synthetic datasets were conducted on a workstation. For real-world datasets, we evaluated them on a powerful Newman machine. We first look at the overall effectiveness and efficiency. As is shown in Figure 4a, state-based strategies yield better recall due to fine granular shading. Figure 4b illustrates that input-based techniques yield higher throughput. Hybrid approach strives for both higher recall and higher throughput. From Figure 4c, 4d, and 5a, we can observe that hybrid approach prefers state-based shading for relaxed latency bound. For tighter latency bound, it prefers input-based shading. There is a turning point at 500 microseconds. Above 500 microseconds, state-based shading takes the lead. Below 500 microseconds, input-based shading takes the lead. That is for the average latency bound cases. The same trend is also observed in the 95th percentile latency bound, as is shown in Figure 5b. Next, we evaluate the effectiveness of shading data selection compared to the four baseline approaches. Input-based shading with our cost model yields better recall than random-based and selectivity-based input shading. The same for state-based shadings. We now evaluate the impact of variance of query selectivities. We control the variance by value distributions. The recall is not affected, and hybrid shading leads to the highest results. For low variance, as x equals 2, the hybrid approach precisely assesses the utility of input tuples and discards irrelevant ones, significantly improves throughput up to 120 times. Next, we investigate the impact of temporal granularity. We can conclude that increasing number of time slices improves recall for hybrid shading, but decreases the throughput. We also consider the impact of cost model estimation. Generally, recall is not very sensitive to the number of clusters. More clusters lead to higher recall, but only until reaching a certain number. In this case, that is 8. We also tested the adaptivity of the cost model. We consider the worst case setting, that is, to change the distribution of attribute values upside down. So we reverse the costs. The quality of query results suddenly drops to 0 and gradually converges to a normal level. Convergence is quicker for smaller time windows due to a shorter lifespan of partial matches. Finally, we examine 2 real-world case studies. One is New York Back City sharing, and the other one is Google cluster monitoring. They have the same trend as evaluating synthetic datasets. Hybrid shading yields highest recall. In back sharing, the throughput of hybrid load shading is comparable to state-based approaches. However, in Google cluster monitoring, it is comparable to input-based shading. After a further investigation, we found that this is because back sharing prefers state-based approaches. However, Google cluster monitoring prefers input-based counterparts. It reveals that different applications may favor different load shading strategies because of their own characteristics. We now conclude our work. First, we present a hybrid load shading for complex event processing. The second, we propose a cost model for hybrid load shading. Thirdly, based on this cost model, we develop efficient decision procedures for hybrid shading. Next, we also discuss implementations considerations, including cost model granularity, its estimation and adaptation, and approximation approaches. Finally, we evaluated our approach using synthetic as well as real-world datasets to prove its efficiency and effectiveness. And that's all. Thank you. Thank you very much. I'm happy to answer any questions.